Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 24, part 1. In this lecture, I will be designing one more cold storage pertaining to positive temperature applications. So, design a cold storage to store mixed vegetables. So, the given product is vegetable. In the previous lecture, we have designed the cold storage for storing 5,000 tons of potatoes. So, the conditions given are: outside condition is 45 degrees centigrade dry bulb and 25 degrees centigrade wet bulb. Product storage condition is 2 degrees centigrade dry bulb, 90% RH. Product loading temperature is 25. Total quantity of product stored per room is 500 tons. Number of rooms is 4. So, the total quantity of product is 500 into 4, 2000 tons. Specific capacity above freezing is given. Freezing point of the product is minus 0.6 degrees centigrade. Dimension of the room is given, length, width and height. Product pull down period is 24 hours. Compressor running is 20 hours per day. Insulation is expanded polystyrene. For the previous problem, it was given puff polyurethane foam. For this problem, the insulation material is expanded polystyrene. Thickness of the insulation is 120 millimeter. Respiration heat load is given. Number of fans 2 of each 1.1 kilowatt power rating. Number of occupants 2. Lighting intensity is 7.5 watts per meter square. Safety factor is 10%. So let us design the cold room step by step. So like previous lecture, I will be writing some of the data, not the entire data which are given in the problem. Given data. Product is mixed vegetables. Insulation extruded, or let us check extruded polystyrene or expanded, because there are two polystyrenes are there. Expanded polystyrene. Thickness of the insulation is given as X is equal to 120 millimeter, which is equal to 0.12 meter. Dimensions of the room are given. Room dimensions. Let us look at the dimensions of the room. 25 by 18 by 12. 25 by 18 by 12. 25 meter by 18 meter by 12. This is length into width into height. Product loading temperature is given, that is T1. T1 is equal to 25 degrees centigrade. Freezing point is given, minus 0.6 degree. Minus 0.6 degree centigrade. Let us check. So product loading temperature is T1. Storage temperature is 2 degrees centigrade. So the cool and the freezing point is minus 0.6 degrees centigrade. But since the storage is pertaining to positive temperature application. So, we will be calculating only the sensible heat above freezing. So, here it is, no need to write this freezing point. So, the product is cooled from 25 degrees centigrade to 2 degrees centigrade. So, that I will take it as TF, above freezing storage temperature. So, let us calculate the various components of heat load one by one. So, first one is transmission load. Transmission load QT, that is equal to U into A into delta T. Delta T also we can write outside condition I think it is 45 degrees centigrade dry bulb. Outside condition or outside temperature, we will write 45 degrees centigrade. Inside condition, that is temperature 2 degrees centigrade. It is given in the problem. So, the outside temperature is 45. Storage condition, that is the cold room temperature, is 2 degrees centigrade. So, this is the delta T for the transmission load. So, this is equal to U is K by X into area into delta T. So, this is equal to K by X, area is 2 times, let us write it in this step itself. K by X, A is equal to 2 into length into width plus width into height plus length into height multiplied by delta T. So, the K value is not given. As usual, we have to refer the cold storage design handbook. So, from ISHRE cold storage, even though it is a repetition for every design problem, I will write in detail from the data book which table corresponding to which value we are taking the value, so that it will be easy for the learners to understand. Cold storage design guidebook, that is table number 2.1, I think. And this is SI unit. The given insulation material is expanded polystyrene. The third row is extruded. This is expanded. This is expanded polystyrene. And the value of K is 0.037. So, it is in watt per meter Kelvin. So, this is table number 2.1. Table number 2.1. Table 2.1. For expanded polystyrene, K is equal to 0.037 watts per meter Kelvin. Watts per meter Kelvin. So, now substitute this value, substitute all the values. Therefore, transmission load is equal to K is 0.037. Thickness of insulation is 0.12 meter. Dimensions of the room are given. Length is 25, width is 18, height is 12. So, 25 into 18 plus 18 into 12 plus 25 into 12. Delta T is the temperature of the air outside and the temperature of the air inside the cold room, that is inside the stored condition. 45 minus 2. 45 minus 2. When we calculate, the transmission load comes to, this is product load. Transmission load, see here I have taken the value of K as For all the numerical questions or a design problem, I have given the solution in the PPT also. In case if the learners want to refer the PPT, you can stop at that particular slide and you can refer the solution, detailed solution. But at the same time, I am explaining and writing. I am writing while explaining the while solving the numerical question step by step. So the transmission load comes to 26.8 kilowatt. 26.8 kilowatt. Now let us go to the next load, product load. Since the storage is above freezing, we need to calculate Q1 and Q4 only. Q2 and Q3 will be equal to 0. So sensible heat above freezing, that is Q1, which is equal to M into Cp into T1 minus Tf. T1 and Tf are given here. T1 is 25 degrees centigrade. Tf is the storage temperature. We should not substitute the freezing point because the product is stored above the freezing point. Since to maintain uniformity in the formulas T1 minus Tf, I am using the same symbol Tf. Here it is not for positive temperature application. We should not take the freezing point temperature. We should take the temperature which is above the freezing point, up to which temperature the product is cooled. Here the product is cooled from 25 to 2. So T1 is 25 and Tf is 2. Before that, we have to calculate the mass of the product. Here if you see, assuming the loading rate can be maximum 5%, normally it is assumed 4%. Assuming the load need to be 4% of the total capacity, M is equal to 4% of, it is given 500. This 500 is given in the problem. Total quantity of product stored per room. Number of rooms are 4. So total 2000 tons. So in one room they are storing 500 tons. So M is 4% of the capacity of a room. M is equal to 4% of storage capacity per room, that is equal to 4 by 100 into 500 tons. So it comes to 4 by 100 comes to 20 tons. So M is equal to 20 tons, which is equal to 20 into 1000 kg. 1000 kg. Cp of the product is given above freezing. Let me write that also. Specific capacity of the product above freezing is given. Specific capacity of the product above freezing is 1.9 kilojoule per kg Kelvin. So let me add this also in the given data. Cp equal to 1.9 kilojoule per kg Kelvin above freezing. Unless it is a negative temperature application, there will be only one specific heat capacity. There is a negative temperature application, there will be two specific heat capacity. One is above freezing, another one is below freezing. So now let us calculate. Therefore, Q1 is equal to M is 20 into 1000. Cp is 1.90. Delta T, the cooling is from 25 to 2. So here we can write in bracket cooling from 25 degrees centigrade to 2 degree centigrade. This is very important. If we calculate the sensible heat load comes to, so 20 tons multiplied by 1000, Cp is 1.9, 25 to, it comes to 87,000, sorry, 8,74,000 kilojoule per day, because this is per day. The 4% of total storage, 4% of total storage capacity, which is the loading rate, it is per day. 8,74,000 kilojoules per day. So this is per day. So we can convert it into kilowatts. So this is equal to 8,74,000 divided by 24 hours into 3,600 seconds. That will be in kilojoules per second, which is equal to per room per day. So this is 10.1 kilowatts. 10.1 kilojoules per second or kilowatts. Next one, Q2 is equal to 0 and Q3 is equal to 0 since the product storage is above freezing. It's above freezing. So Q2 and Q3 are 0. So we'll calculate the value of Q4, then we will find out the product load. Q4 is the respiration load. Mixed vegetable is a live product, so which will have the respiration load, that is Q4. So that is equal to the total quantity multiplied by the heat of respiration. I think H of respiration is given. It is given as heat of respiration is given as 1.9 kilojoule per kg per day. 1.9 kilojoule per kg per day. So heat of respiration is given. Let me write it here. This is H of respiration is also given, 1.9 kilojoule per kg per day. So the total quantity is 500. So here I am not subtracting the 20 tons which is already taken. So we assume the total quantity, the respiration load is calculated assuming that the entire quantity are in the store and the refrigeration load is calculated at the last day of the loading. So it is 500 tons into 1.90, which is equal to 500 into 1000 into 1.90. So this is equal to Q4 is equal to, again this also comes to per day. So 9,50,000 joules per day. 95,000. It is kilojoules per day. It should be kilojoules per day. So it comes to convert the kilojoules per day into kilowatts. Kilojoules per day. So which is equal to 9,50,000 divided by 24 into 3,600 kilojoules per second or kilowatts. So it comes to, the respiration load comes to 11 kilowatt. 11 kilowatt. Now let us calculate the total product load. So therefore the product load is equal to product load Q suffix P is equal to Q1 plus Q2 plus Q3 plus Q4. So this is Q4. Okay, the letter is not clear. So Q1 is 10.1 kilowatts. Q2 and Q3 Q2 and Q3 are 0. Q4 we have calculated just now 11 kilowatt. So the total product load comes to 21.1 kilowatt. So I will stop this lecture at this point. So I will be continuing with the infiltration load, occupancy load, lighting load, equipment load in the part 2 of the lecture number 24. Thank you.